Alrighty folks, welcome to week 2 of our online classes. This week we will be covering heat, chapter 8. So, as usual, we'll come off the top with a very broad question. What is heat? Well, fundamentally heat is just the energy of particles. Everything is made out of particles. And we usually break these into states of matter, solids, liquids, and gases. And so we think about heat, the amount of heat something has, or its temperature. That's really just a reflection of how much energy the particles of that substance have. So when it comes to gases, the temperature of, say, air, if it's hot, those particles are zipping around really quickly. When it's cold, the particles move around slowly. And that's easy to visualize for gases, but what about liquids and solids? Well, liquids, they can move around a little bit more. You can almost imagine, say, like two particles attached by like a spring, for instance. That's sort of what, say, like a liquid is. Water is a bunch of particles that are kind of hanging on to each other. And those particles bounce around a little bit more when they're hot, and they're a little more stable when they're cold. But even solids, like my desk, they're made of particles. Solids are comprised of particles, and if they're hot, those particles, even though they're stuck in place, jiggle around a little bit more. When they're cold, they jiggle around a little bit less. And we see this physically in the way that solid objects expand and contract. So, recapping, how much something moves, that determines its temperature. Temperature is a reflection of the energy of individual particles, which is how much they move. More heat means more energy, which means more motion, specifically velocity. There's a way of defining temperature as the root mean square, sort of an average velocity of the particles. The air temperature is really just the average velocity, a reflection of the average velocity of the particles in the air. And then similarly, if you have less heat, it means you have less energy, and that becomes less motion. And as I said, gases move. Physical objects might expand or shrink as their temperature is changed. Well, that brings us to how we measure temperature. So you guys, having grown up in the United States, or at least most of you, I assume, grew up in the United States, you're probably used to measuring temperature with degrees Fahrenheit. Degrees Fahrenheit is probably your familiar unit of temperature, but there are a couple of other ones as well. There are degrees Celsius, and then Kelvin. Kelvin actually doesn't have the word degrees, though you might even find me sometimes accidentally saying degrees Kelvin, because it is a measure of temperature. But we have degrees Fahrenheit, degrees Celsius, and then the Kelvin scale. So let's just look at a few common points to give you guys a reference, because as I said, you're probably familiar with the Fahrenheit scale, but as with most things in this class, we're going to be using units you're less familiar with. We're going to be using degrees Celsius and then sometimes Kelvin. So, where did these things come from? Well, somebody at some point had to originally define a temperature scale, and they had nothing to go on. This is something that was never done before. You know, people knew things were hot, people knew things were cold, but actually ascribing a number to it was something that had never been done before until these people decided to try to create a temperature scale. So Fahrenheit and Celsius did these things a little differently. Fahrenheit just decided to make 0 as cold as he could possibly get it. And at the time, that was just adding salt to water and then dumping in ice, trying to get water as cold as he could possibly get it, and that's what he ended up calling 0. Now, that's not really where water freezes on the Fahrenheit scale. Water freezes at 32 degrees, but the coldest he could get water was what he called 0 degrees, and he called 100 degrees human body temperature. Now, it turns out that it's more like 98.6 degrees Fahrenheit with our modern measuring tools, but that was roughly how the Fahrenheit scale was created. 0 was the coldest you can possibly get water, 100 was a human's body temperature. Well, this gave us a lot of sort of clunky numbers then. As I already mentioned, 32 degrees is where water freezes, 212 degrees is where water boils. Our body temperature is close to the 100, 98.6 degrees, and room temperature is 72 degrees Fahrenheit. Celsius approached it a little bit differently, maybe a little more, in my opinion, it makes a little bit more sense because Fahrenheit based it off water and then humans, two somewhat different things. Celsius at least based 0 and 100 on water, 0 being where water freezes, 100 degrees Celsius is where water boils, and then a linear scale in between. Where common things fall, 37 degrees would be your body temperature in Celsius, 22 degrees is room temperature in Celsius, and these numbers are common. They might come up in some homework problems or other examples. On a test, of course, I would still give you the exact number. I wouldn't just say room temperature and ask you to remember that it's 22 degrees Celsius. But now you guys have a rough idea of how to compare these scales. These are just 4 important numbers on both scales of Fahrenheit and Celsius. So you can have a quick mental conversion back and forth. But for our purposes, we're going to be working problems in Celsius. All right, so here are the exact scales between these two things. Now, this isn't a unit conversion in our traditional sense where we sort of multiply by one number to get to another number. It's really a mapping. For every degree in Fahrenheit, there's a corresponding degree in Celsius, and it maps according to this pair of equations. So if you have a number in Fahrenheit, you subtract 32, you then multiply all that by 5 over 9. That gets you the corresponding temperature in Celsius. Alternatively, you can start with the temperature in Celsius, multiply by 9 over 5, add 32, and that gets you to a temperature in Fahrenheit. You may have to use these a couple of times, but in general, we're not going to be using them much. We'll just work within Celsius. We're not going to convert back and forth a whole lot. However, there is something fundamentally flawed about both of these temperature scales. Both Celsius and Fahrenheit have negative values, and that doesn't work well in ratios, which we'll see next chapter. We'll start taking temperature ratios. And for this reason, scientists created the Kelvin scale, and Kelvin is based on absolute zero. So we talked about how more heat means more energy means more motion, and similarly less heat, less energy, less motion. Well, imagine a temperature so cold, even atoms themselves don't move. Now, this hasn't actually been achieved. I'd have to double check what the lowest temperature is. It's something silly in terms of how many zeros, 0.00000 something degrees Kelvin. Did it? Not degrees Kelvin, just Kelvin. But anyway, Kelvin was defined on having an absolute zero. So any temperature must be bigger than 0, and you can make ratios. So if it's, 40 degrees Kelvin, that is twice as warm as 20 degrees Kelvin. How many times warmer would, say, 32 degrees Fahrenheit be compared to negative 40 degrees Fahrenheit? Well, you can make a ratio, but it's going to be like negative something. Would you say something is negative times warmer? It just doesn't make sense. And that is why we had to create the Kelvin scale. Kelvin is conveniently related to Celsius by just adding 273 degrees. Whatever your temperature is in Celsius, you add 273. That gets you to a temperature in Kelvin. Obviously then, negative 273 degrees is actually the coldest you can get in degrees Celsius. You cannot get colder than negative 273 degrees Celsius. If you were, you would end up in negative Kelvin, and Kelvin was created to not have negative temperatures. So that's a basic introduction to heat. In our next video, we will talk about the transfer of heat.